Hello all, in this lesson we're going to be preparing ourselves for the Unit 6 Modern Physics exam. Number 1, it asks about the wave-particle duality of nature, and it wants to know when it would be most apparent in analyzing the motion of like a given particle or such and such. So the wave-particle duality is most noticeable on the smallest scale, such as on the scale of an electron or a photon. So that means that my answer for number 1 is choice 4. Number 2, experiments performed with light indicate that light exhibits. So I put in a couple of examples, and I just said that the photoelectric effect, where a photon comes in and dislodges an electron, is particle behavior evidence. But we have several other wave behavior evidences, such as diffraction, refraction, and Doppler effect. So I think the best answer choice here is both particle and wave properties. Which graph best represents the relationship between energy and mass when matter is converted into energy? The relationship between E and M is considered direct, and would, of course, be best answered with choice 1. Number 4. The energy produced by the complete conversion of this small number of kilograms of mass into energy. It would be best defined using the equation E equals mc squared. There's my mass, and the speed of light squared is 9 by 10 to the 16. When you multiply those two together, you're going to get 18 times 10 to the, and in that case it's going to be 16 minus 5, or 11. Which is the same thing as 1.8 times 10 to the 12, which is, of course, the same thing as 1.8 megajoules. And that's because a mega means 10 to the 12. So 3 is my answer. In number 5, we have a variable frequency light source emitting a series of photons. And as the frequency of the photon increases, what happens to the energy and wavelength of the photon? So we know from the unit that E equals HF, and we also know that E equals HC over lambda, but what we're really doing here is we're saying that F is C over lambda. We want to know essentially the relationship between the frequency, the energy, and additionally, the wavelength. So there's a couple of things that are going on. When frequency goes up, energy is definitely going to go up. So I can immediately eliminate choice 1 and choice 2. Choice 3 and 4 are the only ones that are reasonable in terms of them saying that energy increases. But the wavelength is going to get shorter if the frequency increases. If you can't see that in this equation, then look at this one. Here you can see that if velocity stays constant, then an increase in frequency will be a decrease in wavelength. So the best answer is 3, the energy increases and the wavelength decreases. Number 6, we have a spectrum of visible light, and it produces blue, green, red, and violet lines. What characteristic of light determines the amount of energy carried by a photon of that light? Generally, this is just going to be frequency. And that's because of Planck's equation, E equals HF. If frequency goes up, the energy goes up. If frequency goes up, the color changes. So there is an association between the color of light and the energy it has. In the next question, number 7, we're asked, a photon of light traveling through space with a wavelength of this many meters has an energy of. So we're relating energy to wavelength, and I recommend this equation, which does show that there's an inverse relationship between wavelength and energy. So Planck's constant is 6.63 by 10 to the negative 34. 3.0 times 10 to the 8 is the speed of light, and the wavelength has been stated as 6.0 times 10 to the negative 7. And when you try to solve those multipliers, you will get 3.31 times 10 to the, and it's going to be negative 34 plus 8 plus 7, so negative 34 plus 15. And I'm getting 19, negative 19. So that's what I'm getting as the energy, 3.31 times 10 to the negative 19 joules. For number 8, we have an X-ray photon colliding with an electron in an atom, which ejects the electron and emits another photon. So here's my photon. It's colliding with an electron, which sends the electron off with a new momentum, but it also produces a new photon with a new frequency. So essentially, the first photon and electron, this photon had a lot of energy because of its frequency being high, and this photon has less energy, which is required because some of the energy is now the kinetic energy of the electron. But during this collision, you do have a conservation of momentum, which is how we can make a claim like this. And additionally, you also have a conservation of energy, which is something that we know from earlier lessons. So both momentum and energy are both conserved. In number 9, it asks about basically the definition of a photon of light. And a photon of light is like a little wave packet, but it really, it has energy and it has momentum, but it does not have mass. So my best answer here would be 3, both energy and momentum. In number 10, it says compared to a proton, an alpha particle has. So in the last one, we're comparing an alpha particle to a proton, its mass and its charge. And you can see in the symbols I've included here, where masses exist on the top, that an alpha particle is definitely more massive than a proton. So you can see here that the mass of the alpha is 4 and the mass of a proton is 1. So that means that the answer has to be choice 4. But we can also prove that the charge is twice on an alpha, because here's the charge 2, and then for a proton it's 1. So it's definitely number 10 being choice 4. In number 11, we have a question about Ernest Rutherford and his alpha particle experiment that was directed at a thin gold foil. And the thing that caused the scattering was that the protons were pretty small compared to the size of the atom in general. And in addition, the alpha particles had positive charges and the nucleus had a positive charge as well, as you can see. So the best answer choice here would be something like 3 or 4, because they both say positively charged. And we would say repelled by the gold's positive atomic nuclei, and then 4 is my final answer. For number 12, we have a model of the atom in which the electrons can exist only in specified orbits. All right, so the specified orbits thing means that we're talking about the Bohr model of the atom, where the electrons are like planets orbiting around the sun. For number 13, we have an electron in a mercury atom, and it's dropping from energy level I to the ground state. So again, from I all the way down to the ground state. And the difference in energy between those two is 10.38 minus 1.56, which gives you an 8.82 electron volt difference. And that means that the photon would also have that energy. For number 14, it says the bright line emission spectrum of an element can best be explained by. All right, so the bright line emission spectrum is when the electrons in orbitals are returning to their ground state and releasing energy. And the only answer choice that really comes anywhere close to that idea is choice 1. In number 15, the standard model of particle physics. We have a meson here, and this is from your reference table. So you can see here in this diagram that mesons will have 1 quark and 1 antiquark. So the best answer choice here is choice 2. And in number 16, this is about this mysterious lambda particle, which contains 1 up, 1 down, and 1 strange quark. And the question wants to know how we could classify that lambda. So since all baryons have 3 quarks, just like this guy, then we would definitely call it a baryon. So I'll just write 3 quarks beside it. And they want to know what's the sign and charge in coulombs of an antiproton. So a regular proton in coulombs would have a charge of 1.67 times 10 to the negative 19 coulombs, positive. But an antiproton, of course, would be negative 1.67 by 10 to the negative 19 coulombs, which is the charge of an electron, by the way. And they also want to know, no, that's it. They just want the sign and the charge. So this must be the answer. All right, number 18. Which statement is true of the strong nuclear force? It's definitely not number 1. The strong nuclear force actually acts only over very short distances, but it does hold protons and neutrons together, so choice 2 is our best answer. So for number 19, which asks me about the tau neutrino, the muon neutrino, and the electron neutrino, I found them all here, electron neutrino, muon, and tau. They all have a charge of 0, and they're all considered leptons, so I don't see any reason to choose anything but choice 1. For number 20, they're asking about charges that mesons may or may not have. Now, mesons and baryons will actually both have the same set of 3 allowed charges, and the 3 allowed charges for mesons and baryons are 0, -1, and +1 E. So the one that's not allowed of these 3 is choice 2, which I guess I should just say is our answer. And 21, which combination of quarks could produce a neutral baryon? And so we want this to be 0, so that you should really just be thinking of, you need 1 from the top row and 2 from the bottom row. So I think that our best answer choice is going to be choice 3, charm down bottom, because the charm will give you positive 2/3, down -1/3, bottom -1/3, and that'll come out to be 0, which will give you your neutral baryon. Now in 22, they want to know which of the following contains quarks. So it would have to be either a baryon or a meson. So don't choose any leptons. Positrons are leptons, and beta particles are essentially electrons, so those are leptons as well. Gamma rays are energy, not particles, so the only answer would have to be alpha particles. And 23, all photons in a vacuum have the same, this is a fact, speed. All electromagnetic waves travel at 3 × 10⁸ meters per second. So it isn't just light that travels at that speed, but radio waves, gamma rays, microwaves, all of them, they all travel at 3 × 10⁸. All right, number 24. Light of wavelength 5 × 10⁻⁷ meter consists of photons having an energy of. So we're going to be looking at the relationship between energy and wavelength again. We need Planck's constant, which is 6.63 × 10⁻34, the speed of light, which is 3 × 10⁸, and the wavelength, which is 5 × 10⁻⁷. And when I multiply just the multipliers first, I get 3.978 times 10 to the, and we're going to be doing a -34 plus 8 plus 7, which gives you a 19 as your exponent, and this of course would be in joules. So the best answer is choice 3, 4 × 10⁻19 joules. All right, number 25. Base your answer to the following question on the mercury atom as it moves from level I to level A, emitting a single photon. So the energy of the photon that it releases would really just represent the difference in energies between I and A, and level I has -1.56 electron volts, whereas level A has -10.38. So we just find the difference between those two. And of course you get 8.82 electron volts. Final answer. For number 26, the energy equivalent of the rest mass of an electron. So I first need to look up the rest mass of an electron on the reference table, and I get 9.11 × 10⁻31 kilograms. We need to multiply that by the speed of light squared to enter it into the E = mc² equation. And the speed of light squared is 9 × 10⁻16. So when I just do those multipliers, I get 81.99 times 10 to the -31 plus 16 would be -15, and this would be in joules. So in terms of scientific notation, it's going to be 8.2, we will say, times 10 to the -14 joules. Final answer, and that is choice 2. All right, for 27, we have this whole like table here, which we've seen before. It just gives you the masses of these particles, which you can also find up here in an equation. And they want us to determine the difference between the total mass of the reactants. So they want us to compare the sum of the masses here to the sum of the masses here. And they just want us to write that difference down here. So let's get started on that. The hydrogen and the lithium weigh 8.02383 universal mass units on their own. And then we also need to grab the masses of two alphas. And alphas have this much mass between them. And they weigh 8.0052 in total. Now, when you do a subtraction between these two numbers to find out their difference, here's what you get. 0.01863 universal mass units. That would be my final answer. Now, for the next question, they want us to take this answer in universal mass units and convert it into mega electron volts, and that's a conversion. Our reference table tells us that every universal mass unit has a mass of 931 mega electron volts in its energy equivalent. So we just need to do a pretty simple conversion to figure out how many electron volts this little mass up here is. So we'll start with our given, 0.01863 U, multiplying it by a conversion factor whose denominator is universal mass units and whose numerator is mega electron volts. And then we just need to fill that in. So, oh, it was not an E, it was a U, my bad. So there's one universal mass unit, 931 mega electron volts, and we just multiply this number and this number. And I got 17.34 mega electron volts, final answer. Last question on this page, 29, about the tau lepton. And they want us to show how this reaction obeys the law of conservation of charge by indicating the amount of charge on each particle. So I know I would need this reference table because I just don't know like what all these symbols mean or like what their charges are offhand. So when I see this symbol, that's a tau, and I can find it over here. The tau is a -1 charge. And additionally, the E is an electron. You can find it here, and it's a -1 charge. And we're moving further with this V bar E. You can find that here, sort of. It's an electron neutrino would be a charge of 0, but this would be an electron antineutrino. Its charge would still be the same, though. It's only going to reverse its magnetic moment, not its charge. So we can say 0 for that. And then that last one, the VT, this is the tau neutrino, and its charge is also 0. Now, the way that this shows the law of conservation is that we have a total of -1 on the left and a total of -1 on the right. Moving on, we have a photon with a frequency of 5.02 by 10 to the 14 hertz, and it is absorbed by an excited hydrogen atom. This causes the electron to be ejected from the atom, forming an ion. The first thing they want us to do is to convert this frequency into an energy in joules. So let's use the equation E equals HF, where Planck's constant is 6.63 by 10 to the -34, and the frequency is 5.02 by 10 to the 14. And if you just do the multipliers first, you get 33.3 times 10 to the -34 plus 14 is going to be 20, 10 to the 20th. Excuse me, that would be -20. And we need to convert this to proper scientific notation, which would be 3.33 times 10 to the -19 joules, of course. We also need to convert this energy into an energy in electron volts. You could do this by converting from joules to electron volts if you follow this basic strategy below. So you have the given information shown in the leftmost area, but you need to take the unit that's displayed here and display it in the denominator as well. So I'll put a joules down here, and then I'll put the unit I want in the top, which is electron volts. Then I just need to go to the reference table and find out how many electron volts are in a joule or vice versa. And I was able to find that 1 electron volt is equal to 1.6 by 10 to the negative 19 joules. So at this point, let's just do the 3.33 divided by the 1.6. And I'm getting 2.08 times 10 to the negative 19 minus negative 19 is 0. So 10 to the 0 is 1. So I'll just take that out. And the answer would be 2.08 electron volts. And then in the last question, you have to remember that this electron was being ejected by the atom, and it didn't tell us where it was starting, but we do know that it's only gaining a possible 2.08 electron volts, and we have to get to ionization. So the farthest we can go from there is, it looks like n equals 3, because at n equals 3 you have a negative 1.51 electron volts required to get from n3 to n infinity. And if you went down to n2, for instance, you would need 3.4 electron volts, which we simply don't have. We only have 2.08. So my answer would be n3 is the absolute lowest. And our last question in this review is, if a proton were to combine with an antiproton, they would annihilate each other and become energy. Calculate the amount of energy that would be released by this annihilation, and this is going to be an E equals mc squared. The trick is going to be to figure out what is the mass of a proton and an antiproton, but if we can find the mass of one of them, then just know that they'll both have that mass, because antiparticles have the same mass as their particle. So I just wrote 2 times 1.67 by 10 to the negative 27, because this I found as the rest mass of a proton, and I'm going to multiply it by 2, because we have the proton and the antiproton. We also need to multiply it by the speed of light squared, which is 9 by 10 to the 16th. And from here, it's a pretty simple solve. When you multiply 2 by 1.67 by 9, you get 30.06 times 10 to the, and it's going to be a negative 27 and a 16, or 10 to the negative 11. But we do need to adjust this to scientific notation, so I'm going to move this decimal, and that's going to give me 3.0. I guess I could say 3.01 times 10 to the negative 10, and this would be joules, and final answer. So that completes the review sheet. Here are the answers in case you need to see them, and good luck with the rest of your studying. I hope you learned something here, and thanks for watching.